This video is about section 8.1, matrices. One of the concepts in this section is the order of a matrix. The order of a matrix is expressed as the number of rows by the number of columns. For example, a 2 by 1 matrix has 2 rows but only 1 column. Here's an example of a 2 by 1 matrix. A 2 by 3 matrix has 2 rows, 3 columns. Here's an example of that. The next concept presented in the lesson is the idea of an augmented matrix. This is a matrix that is connected to a system of equations. Here's an example. This augmented matrix is equivalent to this system of equations. Solution techniques that you've learned about systems of equations will also work for augmented matrices. The next concept in the lesson is the idea of elementary row operations. These are the transformations that can be done to the rows of an augmented matrix without changing the solution to that matrix. Elementary row operations correspond to the transformations that can be done to solve a system of equations. For example, in any equation, you can multiply or divide every term by the same number. That's true about the numbers in any row of an augmented matrix. In a system of equations, you can use the elimination method to create opposite terms that would add together and be eliminated. That's true of the rows of an augmented matrix as well. In this system, if you multiplied the first equation by -1 and added that to the second equation, the y terms would be eliminated. The same idea works with the matrix. You could multiply the first row by -1, creating a -1 in this position, so that when you add the second row, a 0 is created. Applying elementary row operations to create zeros within an augmented matrix is called Gaussian elimination, and it's used to solve systems of equations using matrices. The next concept in the lesson is row echelon form. An augmented matrix is in row echelon form when there's a particular pattern in its leading coefficients. Let's look at an example augmented matrix. This augmented matrix is in row echelon form because the first row has a leading coefficient of 1 and there are zeros under that coefficient. The second row begins with 0 and then has a 1 and there is a 0 under that 1. Notice the triangular arrangement of leading ones. When an augmented matrix has that format, it is in row echelon form. The next vocabulary word is reduced row echelon form. A matrix is in reduced row echelon form when it has the diagonal arrangement of ones, but there are zeros in all other positions. Let me show an example of that. Observe the diagonal pattern of ones, and notice that these are all zeros here, and these are all zeros here. A process called Gaussian elimination is used to change an augmented matrix into a row echelon form matrix. And a process called Gauss-Jordan elimination is used to change a row echelon form into a reduced row echelon form. The reduced form explicitly gives the answers to the system of equations connected to this matrix. The solution to the system associated with this matrix is Z equals 4, Y equals 6, X equals 8. When a matrix is in row echelon form, like this example, it's also possible to find solutions to the associated system using substitution. From the last row, we can tell that Z equals 8. Then using substitution, you could use the second row to figure out an answer for Y. Here's what that would look like. 1Y plus 2 times Z, but remember that Z is 8, is equal to negative 4. Solving this equation, we see that Y is equal to negative 20. Now that we know that Z is 8 and Y is negative 20, we can substitute into the first row of the matrix to find the answer for X. Here's what that would look like. 1X plus 2 times Y, but remember Y is negative 20, plus 4 times Z, but remember Z is 8, is equal to 6. We could then solve this equation to get the answer for X. When using a matrix to solve an associated system of equations, it's common to write the answer as an ordered triple. For example, the solution to a matrix might be 2, 3, 10. An augmented matrix can also have no solution. For example, in the process of performing elementary row operations, it might happen that you create a row that has all zeros and then a non-zero number to the right of the dividing line. If that happens, then there is no solution. It's also possible for an augmented matrix to have infinitely many solutions. That can happen when you have fewer equations than variables. The final thing I want to show in this video is an example of Gaussian elimination and an example of Gauss-Jordan elimination. Let's look at Gaussian elimination first. Here's an example problem. Recall the meaning of this augmented matrix. It has an associated system of equations with 3 variables, x, y, and z. If we can solve this augmented matrix, then we will have solved the associated system. To perform Gaussian elimination, we use elementary row operations until we've created row echelon form. The format that we want to create will have a 1 in the upper corner, a 0 here, a 1 here, a 0 here, 0 here, and a 1 here. It doesn't matter in what order you perform the operations, but it does need to take you to row echelon form. The first row operation that I'm going to perform is to take negative 2 times row 1 and add that to row 2 to create a new row 2. When performing this row operation, row 1 and row 3 will not change. Row 2, however, will change. Negative 2 times 2 is negative 4, and negative 4 add 4 is 0. Negative 2 times 4 is negative 8. Negative 8 add 1 is negative 7. Negative 2 times 3 is negative 6. Negative 6 add negative 2 is negative 8. Negative 2 times 6 is negative 12. Negative 12 add 8 is negative 4. I did not have to choose that row operation as my first step. However, it did create a 0 in this position. My next row operation is to divide row 1 by 2. When performing that row operation, row 2 and row 3 will not change. Row 1 is going to change. 2 divided by 2 makes 1. 4 divided by 2 makes 2. 3 divided by 2 makes 3 halves. And 6 divided by 2 makes 3. The reason I did that row operation is because it creates a 1 in this position. My next row operation is going to be -3 times row 1 added to row 3 to create a new row 3. And I'll write the result over here. When performing this row operation, row 1 and row 2 will not change, but row 3 will change. -3 times 1 is -3. -3 add 3 is 0. -3 times 2 is -6. -6 add 0 is -6. -3 times 3 halves is -9 halves. -9 halves add 5 is 1/2. -3 times 3 is -9. -9 add -1 is -10. The reason I selected that row operation is because it created a 0 in this bottom corner position. Next, I'm going to take row 2 and divide by -7. When performing that operation, row 1 and row 3 will not change. 0 divided by -7 is still a 0. -7 divided by -7 is a 1. -8 divided by -7 is 8/7. -4 divided by -7 is 4/7. The reason I did that operation is because it created a 1 in this position. Next row operation. I will take 6 times row 2 and add to row 3. When performing this operation, row 1 and row 2 do not change, but row 3 will change. 6 times 0 is 0, and 0 add 0 is still 0. 6 times 1 is 6, 6 add -6 is 0. 6 times 8/7 is 48/7. 48/7 plus 1/2 is 103/14. 6 times 4/7 is 24/7. 24/7 add -10 is -46/7. The reason I selected that row operation is because it created a 0 in this position. There's only one more change that needs to be made to create row echelon form. We want to have a 1 in this position. We can accomplish that by taking row 3 and dividing by 103/14. Another way to think of it is take row 3 and multiply by 14 over 103. I'll write the result over here. This series of 6 elementary row operations to create row echelon form is called the Gaussian elimination process. Finally, let's discuss Gauss-Jordan elimination, which creates reduced row echelon form. Let's use the row echelon form matrix from our first example to continue with the Gauss-Jordan elimination process. I want to have a 0 in this position. What number gets added to 8/7 to make 0? That would be -8/7. So as my row operation, I can take -8/7 times row 3 and add it to row 2 to create the new row 2. When performing this operation, row 1 and row 3 will not change. -8/7 times 0 is 0, and 0 add 0 is still 0. -8/7 times 0 is 0, and 0 add 1 is still 1. Negative 8/7 times 1 is negative 8/7. Add 8/7 is 0. Negative 8/7 times negative 92 over 103, add the 4/7 makes 164 over 103. I am, of course, using a calculator that does fractions when I'm figuring out these answers. The next thing that I want to accomplish is for this number here to be a 0. What would you have to add to a 2 to create a 0? You would need to add negative 2, which I can create from row 2. Here's my row operation. Negative 2 times row 2, add row 1. When performing this operation, row 2 and row 3 will not change, but row 1 will change. Negative 2 times 0 is 0. 0 add 1 is still 1. Negative 2 times 1 is negative 2. Negative 2 add 2 is 0. Negative 2 times 0 is 0, and 0 add 3/2 is 3/2. Negative 2 times 164 over 103, add 3 makes negative 19 over 103. The next thing I want to accomplish is for this number to be a 0, which I can cause to happen by utilizing row 3. My row operation will be negative 3/2 times row 3 added to row 1 to create the new row 1. Negative 3/2 times 0 is 0. 0 add 1 is still 1. Negative 3/2 times 0 is 0. 0 add 0 is still 0. Negative 3/2 times 1 is negative 3/2. Add the 3/2 makes 0. Then, negative 3/2 times negative 92 over 103, add the negative 19 over 103. The answer is 119 over 103. Gauss-Jordan elimination refers to the 9 row operations that were performed to create reduced row echelon form. Gauss-Jordan elimination starts by doing Gaussian elimination to create row echelon form, the triangular arrangement of leading ones. But then you continue on to create extra zeros in the matrix so that you only have the diagonal of 1s and all other spots are zeros. The solution to this augmented matrix is z equals negative 92 over 103, y equals 164 over 103, x equals 119 over 103. This process took a long time, and because there were fractions in the problems, it made it even harder to understand. So you might wonder, why would anybody ever want to do Gaussian elimination or Gauss-Jordan elimination? And the reason is because your graphing calculator can automatically do these processes. But your graphing calculator cannot automatically solve a system of equations when the letters x, y, and z are in it. So what a mathematician does is take the original system of equations that has variables, think of it as a matrix which only has numbers, and then uses the button on the graphing calculator that will automatically perform Gauss-Jordan elimination. The calculator will have an answer on the screen that looks something like this right here, and the mathematician knows the answer for z and y and x. If we were still in regular face-to-face class, I would show you how to use your calculator to automatically solve these matrices. But since we're not in regular class, we're going to skip that topic. This concludes the video about section 8.1.